Hi, in this video, we're going to take a look at multinomial models. All right, so when we're doing logistic regression, we've got two levels, something like sick, well, broken, not broken, default, paid, yes, no, true, false, something like that, pass, fail. We've got two levels. Now, we've got plenty of situations where we need to model something that's not two levels. All right, so what we want to do in this video, we want to extend logistic regression to having more levels to deal with. So this could be, state A, state B, state C. This could be, different types of ground cover, which is the example that we'll work on. There are, multiple ways that we could, multiple target variables that we could possibly have. Just that here we're focused where we have three or more. All right, so also we're going to be focused on unordered levels. And so this is not going to be a situation of like high, medium, low. High, medium, low, there's order to it. We'll talk about ordered modeling later. Here we're worried about like there isn't an inherent order on what's going on. Maybe like species of an animal, species, specific bacteria. So it's something like that. That there isn't like I wanted to compare two. I can't say that this one's greater than this one. Now, when we do multinomial model, and this is true for the ordinal version also, is that the more levels we have, in general, the less accurate our model will be. Why is that? Well, think about the situation where I only have two levels. Well, there's only one way I can be wrong, right? There's two possibilities. I got the other way. Now, think about if I had 10 levels. Well, there's 9 ways to be wrong when I make a prediction. Well, 9 ways to be wrong, I have more opportunities to make a mistake. And because of that, in general, the more levels we have, the more or the less accurate our models are going to be. So it's going to be a good idea to bend the levels of our target variable in a manner that jives with our project. All right, so what's going to end up happening is that in real life problems, some of the levels, let's say you have 7, and for the business, really 4 of them are super important and 3 of them really aren't that important. And so what I could do, I could take those other 3 and put them into like an other category and then leave the ones that are super important as is. Now, another option we would have is actually to take those levels that are important, full blown throw them out, and when I make a prediction, we only predict on those 4 levels that are super important. Now, I would be inherently setting it up so that I'm making a mistake on those, but this is an option that we have that it might be that like what's important is so important, we only want to consider the other situations. And when those other situations come up, we'll just accept that our model is incorrect. Um, just an option for you. I've never launched that. I've always just put in the unimportant ones into like an other category, but it might be what you need to do. So that would be when we have levels that are so rare that their impact is negligible, just because it's so rare that the mistake is okay because it's going to happen so rarely, or operationally, those errors just don't matter. All right, so let's go ahead and run through some examples. First, I'm going to prepare my workspace and load my data. All right, I'm going to take the cover type data, which I got from Kaggle. All right, so now let's do some data prep. And so, excuse me, I am going to convert my soil type. All right, so what's going on here is that I took a look at the different soil types, and I went ahead and bend them into 2 levels. I put the ones to me that looked more similar in the data, put them into one group. I put everything else in another. And so now I'm going to have soil type is going to be if it's in this group. So you'll notice that like 27 is not in this group. I've got 26 and 28. You'll notice that I've got 20 and 25, but 21, 22, 23, 24 is not in this vector. All right, so anytime I see these, I'm going to go through and just put in a 1. All the others are going to be a 0. So I bend all of these levels into just 2 levels. Also, I'm going to bend wilderness area, and so that wilderness area 1, wilderness area 2 are a 1, 3 and 4 are a 0. And I'm going to square elevation. I came upon that from doing either Box-Cox or Yo-Johnson transformation. The parameter was close to 2, so I'm just going to have a quadratic. And I'll go ahead and apply Yo-Johnson to these predictor variables. I'm going to create a train validation test split. And I went ahead and all of this stuff that I'm doing here is I'm setting it up so that the row names include the target variable in them. So that way I have it's just easier to judge what's going on as I evaluate what's happening. And here are my predictor variables after I've done my data prep. All right, so let's check the distribution of the target variable. Now I went through and I bend the cover types that are not like major ones in this one. And so what will happen, we can see that approximately half are cover type 2, 36% are cover type 1, and then 15% are all the others. I bend all the low frequency ones into a group. Now, if this was a real project, here I'm saying that these other categories, everything that goes into other, is not as important. Like I don't need to distinguish between these two, but I have to nail it on 2, I have to nail it on 1 for this project. Okay, so first I'm going to go through and I'm going to show you what not to do to kind of help understand like one approach to this. So here, what I'm going to do to get a model is I'm going to go through and for every single level, I'm going to fit a logistic regression model. All right, so I've got 3 different levels. I'm going to have a logistic regression model modeling 2 versus not 2. I'm going to have a logistic regression model for 1 versus not 1. And we have a logistic regression model for other versus not other. Now, we don't want to do this in general, but this is an option for us. I like explaining about this because this is easier to understand mathematically than the other models I'm going to talk about later. I'm basically just repeating logistic regression across the board. All right, so there's some reasons we don't want to do this in general, but it is an option for us. First of all, multiple models are harder to maintain. If I could get a good solid model in one shot, I don't want to have 3 separate models. There are more parsimonious ways to solve the problem that I'll show in a moment. There's better model structures for this purpose if I want inference. And here, one thing is going to end up happening is that pretty frequently when I add, so I'm going to take an observation, I'm going to put it into model 2, model 1, model other, get the probabilities, add them up, it's not going to equal 1. Now we can rescale it, but if I had a good solid model structure, that wouldn't even be coming up as an issue. Right now, conceptually, it's pretty easy to understand, I feel like, compared to the ones of like, the log of the ratio of expected values, which we'll talk about in a moment. Here, this is a very natural extension of logistic regression. I'm just doing it multiple times. I'm creating more predictor variables off of my target. This is very flexible, and if I wanted to, I could have different data prep for each of the different levels. I could have actually different models altogether. I could have do feature selection. This is definitely high flexibility way. And if I want to, for one level, potentially I could have a k nearest neighbors. Another one could have random forest. Another one could have logistic regression. I could do probit regression on another. So there's a ton of flexibility in this. And also, this is a tool in our tool belt when my model isn't good enough, when I'm trying to do the better, more straightforward methods and they don't work out, I can bounce to this just so that I have a way of like trying to crack the problem. All right, so I'm going to create a list of logistic regression models. And for each level of my target variable, I'm going to go through and say create a binary vector of 1 if it's that level, 0 if it's not. So the first go around, level 2 was the first one I had on that bar plot. So I'll have, if it's level 2, 1 or 0 binary vector. If then next go around, level 1, 1 or 0 binary vector, then other 1 or 0 binary vector. Okay, and I'm going to just build this up, and now I've got my model. So here is my logistic regression model for level 2, my logistic regression model for 1, my logistic regression model for other. All right. Let's extract the probability. So I'm going to use sapply to get this out nice and easy. Sapply will go ahead and give me a data frame. And we can see that since I put response here, I've got the probabilities of each one going into this. Now, you'll notice that if you actually go through and start doing the addition, these rows are not, a lot of these rows are, most of them are not going to actually add up to exactly 1. So these are technically not probability vectors. And to resolve that, like here, this is greater than 1. I can go out and just rescale things. All right, so here is a histogram of the values. So 1 is over here, and you can see that everything that's not like in that straight vertical part, that vertical cut, is going to not be exactly 1. It's not a probability vector. And we go from 0.6 to greater than 1.5 for the sum of the probabilities. All right, that doesn't make sense. The sum of the probabilities should add up to 1. All right, so I can just rescale. So for each individual observation, I can take the row of modeled probabilities, divide by the sum. And I'll now I've got actual probability vectors going. These all add up to 1 across the row. Now, something that's nice that when I have the row variables like this, or the row names, you can see that 2 is the correct answer for all of these, and that makes it easy for me to compare those probabilities. Here, other is the correct result, and we can see that the probabilities when it's other, the model probabilities, are not, I mean, they're all correct every single time, but there is still, it's not a big gap between 2 and other. So that's something to be mindful of as I work through my project. All right, so now let's evaluate the model. And so here we can see that overall my accuracy is 66%. So it gets it right 2/3 of the time. Now remember, I would have had a 50% accuracy if I just would have said 2 all across the board. Now, so it is an improvement. It's not a great improvement. If I want to, I can go into the confusion matrix here on the over 7,000 times. The correct answer was 1, but the model predicted 2. 28,000 times, the correct answer was other, the model predicted 2. And so, we can see all of this through and get through sensitivity, specificity, and we can compare all of these. Now, you'll notice that this is a lot to wade through, right? I've got sensitivity, specificity, all of this for each individual level on this. So that's quite a bit. Now, there is another way to compute the probabilities, and that is to use what's called softmax. In softmax, I take the linkage. So for standard logistic regression, I'm going to take the log odds of from the model, and I'm going to take the exponential of the log odds, or the length function if I'm doing probit or whatever, and then add up the exponentials for the individual observation. That's how I'm going to get my probabilities. And so here is the linkage value, the log odds. So it's log odds for standard logistic regression. And so we can just see what's going on. And then I can just go ahead and rescale. So here is the linkage. Here is the exponential of the linkage. are the probability values. So you'll notice that I tend to get more extreme values off of softmax than I do off of the probability ones. The probability approach is the way that's very nice if I want to be able to use different model structures. So if I had, if one level was being modeled with random forest, another one was being modeled with k nearest neighbors, another one was being modeled with stochastic gradient boosting, I will always be able to get probabilities out. For the linkage, I need to have the same linkage structure. So they all need to be like probit or coshit or logit, something like that. And so softmax requires the same overall model structure for us to be able to do this. And let's go ahead and check our statistics. And you'll notice that things are really, really close to what I had before, because where I had the largest linkage is where I have the largest probability estimate. And so the actual classification value did not change. Our model probabilities changed, where softmax says things are stronger than they make it. Softmax makes it look stronger than what the model probability version made it look like. All right, so now let's go ahead and do it a better way. Now this is, so what I talked about previously, I talked about using individual models for each individual level, because that's just an easier, more natural approach conceptually. But in operations, we want to avoid doing that if we can. That way is a good choice. If I can't get the model to be good enough and I need to back off and try something else, but uh, I, uh, I don't want to do that. Instead, I would prefer to use things that are actually just, tailored out of the box, set up for multinomial modeling. And so let's go ahead and use innet's multinom function. All right, so what this is going to do, this is going to fit n-1 levels. All right, so if I had 10 levels, it's going to fit 9, and then it's going to take the probabilities, model probabilities of those 9, whatever's left over is assigned to that last missing one. And this is going to work with the ratio of the expected values to work off of this. So that ratio is, so remember in log odds, we have the probability of success over the probability of failure. All right, so what I could do, I could say that it's the probability of 1 over the probability of 0. Level 0, level 1, level 0. What we're going to do, we're going to have a reference level, and I'm going to have the model the model probability of the reference level will be on the bottom for all of them. So if I had 10 levels, I'm going to have 9 fractions. Levels 1 through 9 will be up top in the numerator. Level 10 will be in the denominator off of that. And this is, an extension of logistic regression in another direction. All right, so the reference level is the level that does not have a corresponding model. And there's going to be k target variables. So there are k levels that we're modeling. We're going to have k-1 modeled values. And then we're going to use the fact that the probabilities sum up to 1 to do the mathematics to get the actual values. And so this is going to give us a system of equations. And we solve. So we have k-1 equations for just the ratios. And then we have the probability sum to 1. This gives us k equations, k unknowns, and we just solve for it. All right, now when I use nnet, we need to make sure that the right-hand side of the formula has scaled 0, 1 values. So I need the minimum to be 0, the maximum to be 1, or you'll just have problems. Nnet really doesn't perform well if we deviate from that. All right, so here you can see that 2 is our reference level for this. And we get our coefficients. And so when it's modeling this, this is modeling the log of the probability of 1 over the probability of 2, the log of the probability of other over the probability of 2, and then use those estimated values plus the fact that the probabilities add up to 1 to do the math to figure out the actual probability. And so, we can scroll through and get our values. This is pretty quick, pretty fast. That's a nice advantage of it. I tend to shy away because of the rescaling requirements. Um, because down the road, I don't like that version of rescaling. All right, we got all these values, and we got our probabilities, estimated for us. So it's doing a pretty good job of spotting two when it's a two, and it's we could also just go with the classification of having just go straight to the class and not worry about it. And now we have a little bit better accuracy than we had before. And so, just, driving home that point, we don't want to do the individual level models if we can avoid it. So this is a bet, this took less work to get going and we get better accuracy. Now, the VGLM package offers a multinomial. This is my preferred way to go when I have multinomial regression, when I want to use logistic regression for this purpose. I feel like this is a good way to go for inference. This has a lot of tools. This package is broad and deep. And so I lean on this one quite a bit. And we go through a very similar point of view. I want to show you the column names in a moment, right here. All right, so here we can see that level 3, the other level, is our reference level. And here we're modeling level 1 probability divided by the probability of level 3 logarithm. So it's like an extension of log odds, and we can get this off. So if I know this value, which is for the first one, 2.7, if I know this value, which is 0.17, and I know that mu1, mu2, mu3 add up to 1, I can sit down and do the pencil and paper arithmetic and figure out what is mu1, what is mu2, what is mu3, and get my model probabilities. And so, we have different kinds of residuals. We've got our working residuals. We have our Pearson residuals. And so here's the response residuals across the board. And we have diagnostic plots to work through. Notice I made sure that I changed the color and the plot character by the classification to help me understand what's going on better. Here's the Pearson residuals. And you can see that this looks a lot like a regular logistic regression, but I have also this middle level floating around. And here is the hat to check for leverage. We definitely have some ones that are proportionally large compared to the rest. Now we can also use GLMNet to use lasso ridge or elastic net. And so here, everything with GLMNet is the same, except for I say the family is multinomial, and the rest is pretty much taken care of for me. And so I use alpha to say, do I want ridge? Do I want lasso? Do I want elastic net? I set up the penalty parameter, and I'll get the results very nice off of this. And you'll notice that I've got, a level 2 and a level 1 and other going on. So this is similar to that multiple models for multiple levels approach. We can get, different diagnostics just like I had before. The output is more complicated, but it's pretty good. If I want to get the modeled class out, when I do my predict, I put type equals class. All right, so for homework, what we're going to do, just take some multinomial target variable data, model it with a couple different models, tell me what you see, post it in Canvas. All right, well, that's all I've got for you. Life is short. Do math.